Thank you very much for giving me this opportunity to speak about an issue that I think is very important. And not only I, climate change has become an important topic of policy discussions in many countries in recent years. And there has been intense but not very productive negotiations between the nations of the world on what to do with the greenhouse effect and climate warming. In the popular discussion about this issue, you hear some people say that climate change is a threat to mankind, probably the biggest threat that we have ever seen. You hear that argument at the same time as other people say that they don't believe that there is any truth in this at all. So what I will do is to give a macroeconomist's view on this issue after having spent some years on the topic, in particular discussing it to a large extent with my natural science colleagues in Sweden and other countries. So what I will do is I will present a simple calculation on the cost of climate change expressed in units of emitted fossil carbon. And that will help us say something about the quantity of this problem and also about what size an optimal carbon tax should be. Should it be more or less infinite, as the ones who argue that this is the biggest threat ever, or should it be zero, as those who think this is not a problem at all would say? So the starting point of the discussion is going to come from both natural science and economics. But the first immediate thing we need to realize is that the ton of emitted fossil carbon mixes quite quickly in the atmosphere, leading to higher carbon dioxide that affects climate change. And I'm going to go into this in a little bit more detail in a few minutes. But the thing is then that this climate change is going to affect the economy all over the world in many ways. And we should note here that the use of fossil fuel has benefits for the users, but as I just argued, it has also effects on other people around the world. And a situation like that cannot be dealt with by the market, and government policy and international coordination is required in a situation like this. So, as I said, what I will do is I will present a very simple and transparent calculation of these external costs of fossil fuel use, and these can be judged to evaluate the optimal tax, but also to say something about how important it is to limit carbon use. And this calculation will be transparent and thus also quite simplified. And I think, though, that there is a great value in actually being so transparent as this one, this formula allows me to be. So the natural science background to the whole problem is that carbon dioxide in the atmosphere affects the energy balance, the difference between inflow and outflow of energy from the Earth as a whole. And the reason for this is that CO2 passes quite easily sunlight, but on the other hand, heat waves that flow out from Earth is much less passed through. And in that way, CO2 acts like a roof in a greenhouse. That's the word greenhouse effect. And this will lead to warming. This effect, that CO2 passes high-frequency light, but not long-wave heat waves, that can, of course, easily be verified experimentally. And it has been known for a long time. The Nobel laureate in chemistry, 1903, so 110 years ago, Svante Arrhenius described this in a paper that he published already 1896. He postulated an approximate relationship between the global mean, global average temperature, and the percentage increase in CO2 concentration. And what he, in the 1800s approximated was that 1% increase in the CO2 concentration leads to 0.06 degrees Celsius increase in the global average temperature. He also then calculated that the doubling of the CO2 concentration would lead to 4 degrees increase in the global average temperature. My colleague, Per Krusell, is also involved in this project. He's a stamp collector, so he wanted me to show this Swedish stamp with Svante Arrhenius on it. In reality, it's not as easy as this, of course. We can experimentally verify the direct greenhouse effect, but there are a lot of more or less known feedback effects, and some reinforce this initial effect and some weaken it. There are some strengthening positive feedback effects. For example, less Arctic ice would reduce sunlight reflection, which then would tend to reinforce the initial effect. More water vapor coming from a heater global climate would also strengthen this, because also water vapor is a greenhouse gas. There are also negative effects like cloud formation. You get more clouds that typically, at least, would lead to more reflection of incoming sunlight and thus have a dampening effect. Airborne particles that we talked about in the introduction is also important. That means that the total effect is unclear, but it's interesting to note that still the best calculation of the sum of all these effects, the feedback effects, is that you get an increase of 3 degrees for every doubling of the CO2 concentration, which is surprisingly close to the Arrhenius old calculation. One should note that the effects here are quite unevenly spread over the world, and they, of course, also involve other measures of the climate than the average temperature, like precipitation and other characteristics. And these will, of course, also be important. This proportional increase, or the proportional relation between the temperature, the climate change on the one hand, and the percentage increase in CO2 concentration is, of course, not that we can be completely certain of. There might be thresholds so that climate change goes faster after some critical levels of CO2 concentration has been reached, but still there seems to be no general consensus on these things. So I would say that the consensus view is still quite close to this proportional relationship between temperature and percentage change in CO2 concentration. So let me now turn to the key question: how should we evaluate the externality induced by emitting a unit of CO2 or a fossil fuel burning how should we evaluate that? And this question can actually be divided up into 3 sub-questions. And the first sub-question is how much damages in flow terms, so per year, are caused by an extra ton fossil carbon in the atmosphere. So that will be the first question we need to answer. The second question is how long time does an extra ton emitted carbon stay in the atmosphere? The longer it stays, the more damages it's going to cause, and the higher should be the optimal carbon tax. The third type of questions we need to answer is how we should evaluate future losses of consumption. Since carbon will stay in the atmosphere for a quite long time, I will return to that in a minute, it's going to cause damages in the future, and how should we evaluate them now when we set the tax? So let's turn to the first question, climate damages. Here, we as economists have to admit that we know less and also have researched much less on the consequences of climate change for the economy. But we should note that the effects are global, as I already mentioned. They come in quite different ways, and they are long run. So the studies that have been undertaken so far have been using two quite complementary approaches. The first one is to study different sectors of the economy: agriculture, forestry, health, coastal erosion, storm damages, and many other different kinds of damages, and study them separately and infer a relation between climate change and effects in these sectors, and then sum them up over sectors and over regions in the world. The second approach is a more of a statistical analysis where natural historical variations in the climate is correlated with economic outcomes like growth in order to get a relation between the economy and climate change. Both these types of approaches leads to a climate damming function, or can be used to find a climate damage function that determines or states the size of damages to GDP for different increases in temperatures. There is, as I already stated, limited knowledge about these things, and of course, in particular, about extreme climate change. So when we do this approximation, we have to realize that here there are substantial uncertainties. We should also note that there are large differences between the effects in different regions, including very large effects in some regions, and even actually moderate negative damages. That is, positive effects in some parts of the world. So that would typically be in the Northern Europe. So Sweden would be a country where, at least according to standard calculations, there would be some benefits of climate change. If we take larger regions or countries like, say, China or the US, there is probably less diversity. And I will show you an example of a damage function that I think is the best that exists for the current being. We should also note that, as we heard in the introduction here, there are lots of other externalities from fossil fuel extraction and the use of that. And air quality and damages to land are, of course, examples of that that's very familiar to any Chinese. There are also other externalities that are at least related to the current use of fossil fuel, namely for transportation, like congestion and accidents. These are very, very important issues, but these more local externalities will not be the focus of this talk. And one should note here that they can be dealt with by national policies and doesn't, as climate change, require international policy coordination. So this is an example of a damage function that we think is, at the current state of knowledge, the best that exists. And as you see on the y-axis, there is percent. So it expresses the percent loss of GDP. And on the x-axis, we have increases in the global average temperature. And the curves are for the US, EU, China, Africa, and for global. Perhaps interestingly, China and the US are on top of each other. So in this graph, there seems to be not much of a difference between the effects of climate change on the economy on China and the US. Always, of course, when I present numbers like this, take it with a grain of salt, since there is fairly limited knowledge. At least there is scope for much more knowledge in this area. We see that the countries here, all of them, China, US, and EU, are substantially below the world, but Africa is quite close to the global average here. So how large is the externality now in terms of the thing that we would like perhaps to tax, namely the use of carbon? So then, in order to answer that question, we need to express this damage in terms of how much an extra ton of carbon changes the climate and then changes the economic outcomes. So we can distinguish here two steps in the mapping from carbon concentration to damages. Namely, first, the step from carbon concentration to climate change as higher temperatures. And then the second step from climate change as indexed by higher temperature to more damages. Here we have noted in our research that the first step has decreasing marginal effects. So the temperature increases less than proportionally with carbon emission because there is a relation between temperature and the percentage increase in CO2 concentration. So when there is lots of carbon in the atmosphere, an extra ton changes the percentage less than when there is little. So this calls for what we call a concave relation with decreasing marginal effects. The second step, on the other hand, from temperature to damages has increasing marginal effects. So damages increase more than proportionally with a change in climate. In the beginning, if temperature and climate change, it doesn't affect the economies very much, but over time, as you get accumulated more climate change or higher temperature, on the margin things become worse. What we have found is that the combined effects of these two steps is approximately a proportional change, a proportional relation, a linear relation, that you can approximate with the following statement: 1 billion ton of extra carbon in the atmosphere reduces global GDP by around 1/400%. Today, we have around 200 gigatons extra of carbon in the atmosphere. So using this calculation, which of course is just a rule of thumb, reduces global GDP by 0.5%. So that's the first question. The second question, how long does carbon stay in the atmosphere? We can first note that the calculation I did on the previous page, if you apply that to global GDP, which is currently something like 70 or 75,000 billions, would, if you translate it to a ton of carbon, imply that we lose $2 every year of GDP in the world for an extra ton. So that's not very much. And here comes then the important thing to note, namely that an emitted ton of carbon stays in the atmosphere for a very long time and causes damages all along. Here we use, again, a simple calculation or a rule of thumb that it seems to be a good representation of more advanced models of how carbon circulates between its different sinks. And this is the approximation. One share, around half, disappears quite quickly to plants and the surface ocean. And with quite quickly here, we mean within a decade or two. Another share, around 20% of emitted carbon, stays for a very long time, thousands of years. And the rest trickles down slowly to the deep oceans, where it makes not much of damages, at least according to current knowledge. And I've used a couple of Greek letters here to represent these parameters, and you will see them soon. So this answers, in an approximate way, the question, how long does carbon stay in the atmosphere? So the remaining question is how to evaluate future losses of consumption. Here we can think of three aspects of that issue. The first is that under the quite reasonable assumption that losses are proportional to GDP, we can note immediately that a larger future economy will be hit by larger damages due to this proportionality. The other thing to note is that if we or future generations are richer, have a higher GDP, their consumption will also be higher, implying that the marginal loss that people experience from a marginal loss in consumption is not so big. If you are rich, losing a unit of consumption is not so bad as if you are poor. The third aspect is how we should evaluate future welfare relative to today's welfare, all else equal. So, for example, with the same consumption. And this is a quite subjective and moral issue that we don't really can use scientific methods to evaluate. What we can then note, finally here, is that larger income in the future, according to aspect 1, leads to bigger losses measured in units of consumption. On the other hand, with larger income in the future, we consume more and don't mind so much losing a marginal unit of consumption. And under quite standard assumptions in economics, these two aspects cancel, implying that the welfare loss of future damages is independent of growth and independent of the future size of the economy. So I was told by the organizers that I shouldn't really use any equations or formulas, but as an economist, I need to admit that I think a formula like this one is quite beautiful, so I wouldn't like to not to show it to you. So this would then be actually the summary of what I've said so far. The damage induced by an extra ton of carbon in the atmosphere, which also would be equal to the tax, is the left-hand side, and we get a formula for how that high it should be. We note that first it should depend on the current global GDP, so the tax should follow GDP, global GDP, proportionally. The second is the flow damage per ton of carbon. I said that a billion tons of carbon in the atmosphere causes a damage of around 1/400%, so that's this parameter. The share of a ton carbon that stays forever is in the numerator of the first term in parentheses, and that is discounted with with the rate at which we discount future welfare. And then we have the share that trickles down to the deep ocean, and here we also discount with the rate at which carbon trickles down to the ocean. So some people like graphs better than formulas. So here's a graph representing the externality cost and thus the optimal tax for different yearly discount rates in percent expressed on the x-axis. And we see that we have from 0.1% per year up to 2% per year. And that's, I would like to note that that's actually a fairly wide range. If we use a subjective discount rate of 0.1% per year, that means that people 700 years out into the future, their welfare is evaluated at around half the welfare of our generation. If on the other hand we use a discount rate of 2%, there is actually a typo here in the slide, I see. The half-life in this sense of intergenerational altruism is not 700 years, it's 35 years, implying that we basically don't care at all, only a millionth of the generations that live 700 years out. On the y-axis, we have RMB per liter gasoline on the axis to the left, and on the right we have US dollars per ton carbon. And we see that the range of the optimal tax, given the calculations I've showed you so far, for the tax expressed in RMB per liter of gasoline is in the order from 2 RMB down to maybe a quarter of an RMB. And often in evaluations like this, a discount rate of around 1% is used, in which case the optimal tax should be maybe 0.3 RMB per liter gasoline. So are these high taxes? I would say that these taxes are relatively low if you compare them to gasoline prices, and probably also if you compare them to other externalities like emission of particles, accidents, and so on. And for the latter, I haven't seen any externality costs done for China, but I've seen them being done for the US and for China, for the UK, and there the externalities coming from other sources like particles, accidents, congestions, and so are in the order of 1.5 to 2 RMBs per liter. I would imagine that in China, these externality costs could even be higher than in the US and UK. When we talk about coal, these numbers are higher. The numbers for the tax is higher in relation to the coal price. The coal price is on the world market maybe a fifth of the oil price. So there you could imagine that the optimal tax is affecting coal use more, substantially more probably than oil use. One can use, and I think that's interesting, our formula also to calculate what we could call the carbon debt. So that would be the discounted value of the future damages that will come due to the past emissions. So we have an excess amount of carbon in the atmosphere. I already noted that that's around 200 gigatons. How much future GDP are we going to lose due to that? And our approximation implies that if we use a subjective discount rate of 1% per year, this carbon debt is in the order of 30 trillion US dollars, or around 40% of current world yearly GDP, or equal to the US and EU GDP combined. It's also equal, by accident, to approximately the government debts in these countries. So this is a substantial amount of money, and of course the issue that might be of interest to have international negotiations on is who should pay for this debt. And this is a matter of fairness, and if we apply reasonable standards, I would say that the polluter pay principle should apply also here, implying that the countries that have done that, which is mostly the rich Western world, should be responsible for this debt. I'm going to be a little quick on tax versus quantity restrictions. First, we can note that if we were to implement a global tax along the ways I've described, that would imply that agents on an otherwise well-functioning market would make the right trade-offs between private benefits and these collective damages. We should note that the formula I derived doesn't make any assumptions on alternative energy, future technology, population growth, and so on. These other assumptions or information would be needed in order to calculate the optimal quotas. And I think that this is a strong argument in favor of using taxes rather than quotas. An example of the problems with quotas is the EU emission trading system, where the price of emission rights have fallen to quite ridiculously low levels due to the fact that we underestimated the cost of reducing emissions. Had we used taxes instead, we wouldn't have had this problem. But of course, one has to recognize also that all polluters are not necessarily under strong market pressure, and that is true in China, and it's also true in other parts of the world. And in these cases, price signals might be less well working. So there is a couple of qualifiers before I end, and this is one that I want to stress, and I've stressed it already several times, that we are not completely ignorant of the economic damages caused by we are certainly not completely ignorant, but about the economic causes of climate change. But there is, on the other hand, certainly a lot to learn, and we do learn continuously. So these formulas that we have derived might be updated. It could also be that we come to a conclusion that there are threshold effects or tipping points, and in such a case, one might take more seriously proposals to have emission quantity restrictions rather than taxes. It's also important to note that I didn't touch at all on subsidies to innovation and R&D. And in general, we know that the market for research and development is not a perfect market. The benefits of the fruits of research is not going to the one who does the research at 100%, and that means that government involvement is necessary. That's also the case for alternatives to fossil fuel, for sure. But there is, in general, the problem with R&D subsidies that it's difficult to know which are the right technologies and who is best at picking the winners, markets or governments. That's an issue that needs to be discussed. An issue that's important to discuss, not the least in China, is whether carbon tax is a threat to growth. And the background to that argument is that we can see that, at least in the short run, energy use is quite proportional to production. So in the short run, the best and perhaps only way to reduce energy consumption and fossil fuel consumption is to reduce GDP, and that's not what we want to do. I want to stress, though, that at least in the longer run, if we extend the horizon to more than a couple of years, perhaps a decade or so, there are substantial possibilities to increase energy efficiency. Swedish energy consumption has been constant since 1973, while GDP has gone up by 75%. Over the last 20 years, on average in the West, there's been a yearly growth in energy efficiency of around 1.5%, slightly lower than, but not much lower than growth. Of course, there is an issue whether we can have energy efficiency growing at par with GDP growth in China, but I would argue that there are substantial arguments for that we can. There is also very large differences in the energy efficiency between different countries. Also in similar countries like the Nordic ones have very large differences in energy efficiency in the order of 5 or 6 to 1. So I argue that in the longer run, energy and GDP can be disconnected. So I will end with some policy proposals or a summary of what I've said. And I first note that the carbon tax is relatively small, and I'm pretty confident that the introduction of an optimal carbon tax in the order of size that I've discussed here would not be a threat to Chinese growth. And I also think that it would be more productive to try to implement an optimal carbon tax in different parts of the world than to continue negotiate on fossil fuel quotas. And here perhaps China could take the lead. And it's possible probably to do it sector by sector and perhaps start by transportation. Another proposal that I already mentioned is that one should think about how to deal with the carbon debt that I was talking about. And perhaps the countries of the world where China could take the lead could push for a global fund where those that have built up this debt should contribute, and the money could be used for R&D and climate and to deal with climate damages in poor countries. So that's what I wanted to say, and I thank you for your time.